welcome you all in the strength of material class. Today I am discussing the long column, and that is Euler's formula, and we are estimating the different conditions for the failure of the column. First I discuss what is column. Column is a long member integrated with the structures, and the member always take axial compressive load, and this is a member axial compressive load along the axis, and this is under when it is in the integrated form, this is subjected to different failures, and these failures we are analyzing here. And for that matter, the columns are this analysis is done by Euler, and this Euler is a Swiss scientist, done in 18th century, the formula, and is widely used for structural design. The columns are, when we do this column analysis, we found that the failures are of different type. This is the stability failure. The stability failure, which is different than what we did the analysis in previous strength of material cases, where mostly they are the stress failure or the elastic failure. Here, the failure is of stability failure, and the column gets buckled, or we can call it the crippled. Now I delete where these columns are being used. It is being used in structure, long multi-storied building, particularly in the bridges, in the aerodrome or airport, and the bridges, airport, and the structures. And this is I have given the four kind of end conditions of the column. This is one kind. This is a long column, and this is the end condition. Here it is a built-in, and this is the free, and this is built-in both cases, both sides, and this is built-in one side, built-in both sides here and here, and this is built-in one side and hinged at one side. So different types of column, and the columns, the definition of column. Thus, columns, the linear length of the member is much bigger than the width of the column or the thickness of the column, and this can, while failing, this is the failure of the column when it buckles or when it cripples. The load is axial is loaded, compressive axial loading is being done along its axis, and the column fails or moves from the lateral directions. And this is the critical load. When this load is being applied, the column buckled, and it is a permanent failure, and we call the structure fails. And we analyze this. This is the formula here for the Euler's. This has been derived from the strength of material, or the deflection formula, d square dy, d square y dx square m by ei. With this formula, we can do this the delta, and this is the y in any section. So this has become the p. This is the section delta minus y. This is the delta minus y is the bending moment, and this is the positive side. This is the positive y, and this is the positive x. So we have second plus sign. So if you integrate it, the formula becomes like that. The P is the critical loads, pi square EI by 4L square. So this is the formula for this Euler's formula for this kind of analysis. Now if you generate this, extended this to the different kind of end conditions, so we modify the formula. Suppose this is for the two hinge condition both sides. If you modify the formula, here one side is the free end and this is the built-in, you will find the deflection line or the elastic line of the member is the half of this. So this is half of this. So this portion is almost like this. So this is the maximum deflection, and this is the fixed. So you revert this and kind that. So L by 2 is this. So it's a very mostly used formula. So we apply this. This we will modify this to apply this formula here. That instead of L, we become L by 2. Instead of L here, we put L by 2 here. So it becomes pi square EI by L square. In this case, This is the when the built inside both sides when apply P here, the critical load becomes like this is the L by 4. This both sides L by 4, in between is L by 2. This L by 4 is of this. So this is the replica of this. This is the replica reverted replica of this. So we can modify this formula into this L by 4. So it becomes like that, 4 pi square EI by L square. So here, this is the condition here. When we apply the load P here, so pi square EI, this is the hinge joint and this is the built-in joint, square EI 0.7 L. So there are different treatments in this textbook. You will read it and refer it to the textbook. So this is the critical load. When when the critical load is applied here, it gets crippled. We call the crippling load or critical load for buckle. The column gets buckled. So it's become distorted. And when it becomes distorted, it will become unstable. When it becomes unstable, we call it a fail. The column failed. And when a column, one of the members of the structure happen to be a column, and if it fails, the whole structure fails. Because other may not fail, but the one failure is that the structure become weaker, and there may be a lot of other failures also. So this is the indicator. This is the full formulae of the Euler's column equations. Now we are analyzing it. One of the reasons we are trying to analyze when we apply the weight, it buckles. What is the stress developed here? We analyze the stress condition of the column. So the P critical by area, if you this is from this equation we have derived it here. P critical by area is equal to pi square EI by A L square. Now I is converting to area into radius of gyration squared. So A cancel, it becomes pi square E by L by R whole square. So this is a new development. L by R is called the slenderness ratio. This sigma critical is equal to pi square E divided by slenderness ratio square. So if we plot this, so we are plotting this. So this relation is being plotted here. And this is we call the stability limit. This equation, if you go beyond this L by R, if you keep on reducing L by R, the column becomes more weaker. If you increase the L by R, the columns become more weaker. Or the stability problem will become very closer to the stability problems or the stability limits. And if you plot this, and there is another limit, is called the strength limit. So what it does mean that the column becomes unstable before it reaches the strength limit. That means the stress developed inside a column is much lesser than the stress, the failure for the elastic failure of the material. So this is one of the findings of our column analysis, that we found that the column becomes unstable or column fails due to the buckling or crippling, due to the stress developed which is much lesser than the strength of the material or the stress required for elastic failure. So we always try to this, and there is a range of, if you go beyond that, there is a range of failures, there is a range of columns. This is called the long column, this intermediate is the medium column, this is the short column. Short column is something. This L by R normally is if we go above 100. If L by R is 100 or above, it becomes long column. If 50 to 100, this becomes short column or medium column. If it is less than 50, it's called short column. In case of short column, the member fails due to the elastic failure or the strength failure.